Hi there, everyone. Like Omar said, I'm Kat, and I'm on the Google Certificate Transparency team based in London. And today I'm here to talk to you all about certificate transparency and how it's helping to make the internet more secure. So, first of all, let's start off by talking about using the web. Let's take an example. Say you're a Gmail user and you want to check your email. What are you going to do? Well, you're going to open up your browser, go to mail.google.com, type in your login details, hit enter, and this web page is going to appear on your computer that probably looks something a little bit like this. Now, the more observant amongst you will notice that up in the top left-hand corner, the beginning of the URL has gone green, and there's this very reassuring little padlock symbol and the word secure. And what this is telling you is that you have connected to the Google servers securely. Now, what do we mean by securely? As you know, it means that all of the information being sent between your web browser and the Google servers is encrypted, so no one listening in on the connection can understand what's being sent. OK, great. So you have this secure connection. But how can you be sure that it's actually Google on the other end of that connection? How can you be sure that it's not just someone pretending to be Google? How can you be certain that when you sign in, you're not really sending your login details to an impersonator? Well, that's where certificates come in. A certificate is something that a web server sends to a web client, like a browser, to prove that they are who they say they are. A certificate contains two very important pieces of information. The first thing is a public key, and the second thing is a domain name or a web address. And a certificate containing these two pieces of information means that if you use this public key to successfully connect securely to a web server, you can be sure that you will get the real version of this website. OK, so for browsers to accept certificates as valid, they have to be signed. And the only entities that are allowed to sign certificates are called certificate authorities, or CAs. So if we go back to our scenario, Google's here, they've got this great website, mail.google.com, and they want their users to be able to connect securely. So they're going to need a certificate to be able to present to browsers so that the browsers will know that they've actually connected to Google. So what's Google going to do? Well, they'll go along to a certificate authority and they'll say, hi, I'm Google. I've got this wonderful website, mail.google.com, and I need a certificate for it. Here's my public key. Please, can you issue me a certificate? And the certificate authority will take this information, they'll have a look at it, they'll run a bunch of checks to convince themselves that this is really Google they're speaking to, and that the information provided is both correct and truthful. And if they're happy with all that information, they'll sign a certificate and issue it back to Google for them to use. Now, this is a really important part of the system. This is the point in the system where there's trust. We trust certificate authorities to get this right. We trust CAs only to issue certificates to the right people. OK, so then, when you go to log into mail.google.com, Google will present your browser with this certificate. And your browser, let's say it's Chrome, will take a look at the certificate, and they'll go, yep, this is a valid certificate, signed by a certificate authority, I believe you're Google, and they'll set up a secure connection so that you can then log into your email and check all of the news. But then, what happens if a bad guy comes along and goes to a certificate authority and says, hi, I'm Google. I've got this website, mail.google.com, that I need a certificate for. Here's my public key. Please, can you sign it? Like I said, we trust certificate authorities to do the necessary checks to know that this is not really Google they're speaking to. But what if, for whatever reason, say they get hacked or they just make a mistake, the certificate authority ends up issuing a certificate that they shouldn't? Well, then, when you go and try to connect to mail.google.com, the attacker could respond instead with this bad certificate. But Chrome will take a look at it, and to Chrome, it's a valid certificate. It's valid, it's signed by a well-known certificate authority. Chrome has no way of knowing that they're not actually talking to Google. So then, Chrome will set up a secure connection. But this time, when you sign in, you'll actually be sending your login details to an attacker. So you're probably sitting there thinking, OK, this sounds a bit scary, but is this really something we have to worry about? Is this actually something that happens in the real world? Yep. One such example is an incident that happened back in 2011 involving a certificate authority called DigiNotar. Now, what happened in this case was DigiNotar was hacked, and the attacker managed to issue a wildcard certificate for the google.com domain. Now, it came out later that DigiNotar did actually detect this attack, quite soon after it happened, but they chose not to report it because they thought they had managed to contain the breach. However, a few months later, users started noticing this fraudulent certificate, and they reported it. And browsers then took the necessary steps to protect their users against these compromised DigiNotar certificates. After some investigation, it came out that the main target of this attack was actually Iranian Gmail users. And in addition to this Google certificate, more than 500 other DigiNotar signed certificates had been issued for a whole host of domains. So clearly there's a problem here, right? And this problem, I've mentioned it twice now, is this blind trust we have in certificate authorities not to misissue certificates. But it's kind of more than that. If they do misissue certificates, we have no way of knowing that that's happened. So what can we do about this? Well, that's where certificate transparency comes in. Certificate transparency is an ecosystem to detect certificate misissuance. Now, I emphasize the word detect because I want to make it very clear we are not preventing certificate misissuance. It actually turns out that's a much harder problem. Within certificate transparency, one key idea is this idea of a certificate transparency log, which is a publicly auditable, append-only certificate store. So what that means is it's basically a big repository of certificates that anyone can add to, anyone can access, anyone can go and see what's in there. Certificate transparency logs can be run by anyone who cares about the security of the internet. For example, Google currently runs 8 certificate transparency logs. Many of the current CAs are running certificate transparency logs. We've had interest from a couple of tech companies who are just in the initial stages of setting up logs themselves. And what would be really great was if there were more big tech companies, maybe like the ones that most of you at this event today work for, that would be willing to also set up certificate transparency logs to help us with this. I'm just going to put that out there. So the goal with these logs is ultimately to have all of the certificates that are used on the web in these logs, so that then, if you're a domain owner, you can monitor these logs. And if you see a certificate for your domain that either you didn't ask for or that doesn't contain your public key, you can take the necessary steps to get it revoked. OK, so before, we had the system where we had certificate authorities just blindly trusted. They could be issuing who knows what, and we had no idea. Now, we've got certificate transparency logs, who are storing all of the certificates that these certificate authorities are issuing, and they're making them publicly available and publicly auditable so we can keep an eye on what's being issued. But what if a certificate transparency log lies about what's in it? What if a certificate transparency log says it's going to store a certificate, but then actually doesn't? What if a log stores a certificate, but then later on deletes it? I mentioned they're meant to be append-only. What if a log decides it doesn't want to be append-only? Haven't we just shifted the trust from certificate authorities to certificate transparency logs? No, we have not. So we can actually verify that certificate transparency logs are behaving correctly. And the reason we are able to do this verification is because of the very cool cryptographic data structure that certificate transparency logs use to store certificates. And that data structure is called a Merkel tree. So the tree you see here is representing a log containing just 7 certificates, C1 to C7, and here. So that's quite a small log. And a Merkel tree is basically just a binary tree where the leaves are the hashes of the certificates. So A is the hash of C1, B is the hash of C2, C is the hash of C3, etc. And the intermediate nodes are the hash of the concatenation of the 2 children of that node. So if we look at the diagram to understand that for a minute, G is the hash of A concatenated with B. K is the hash of G concatenated with H. And that propagates all the way up until we get to the top, where we have what we call the tree head. Now, upon request, a certificate transparency log is required to report its current tree head. And you can use this cryptographic data structure to check that a certificate transparency log isn't lying or misbehaving. And we don't have to just blindly trust it. So one of the examples of misbehavior that I mentioned earlier was, what if a log says it's going to store a certificate, but then actually doesn't? Is there a way that using this we can check for the inclusion of a certificate in a log? Let's take an example. Say we wanted to check that C3 is actually in the log. What could we do? Well, we can calculate C, because from the previous slide, C is just the hash of C3. And then if we could calculate H, and we could then calculate K, and if we could then calculate the tree head, we could then just compare our calculated tree head with the tree head the log is reporting, right? Well, wait a minute. In order to calculate H, we need D. And in order to calculate K, we need G. And then in order to calculate the tree head, we need L. So what this means is for a log to prove that it's included a specific certificate, all it has to do is provide these missing nodes. So as we add more certificates to a tree, and the tree grows, the tree head value will change, right? So there's a similar but slightly more complex proof to this that allows us to prove consistency between two tree heads. I'm not going to go through this proof in the details of this proof in this talk because we don't have time, but there is this proof. And what I mean by proving consistency between two tree heads is that a log can prove that one tree head was created by only appending certificates to the tree represented by another tree head. And as it turns out, these two proofs are all that is needed to check that certificate transparency logs are behaving correctly. And they work. Using these proofs, the certificate transparency ecosystem is currently self-policing, and we have successfully detected 2 misbehaving certificate transparency logs. The log operators of the first log ended up using the same key pair for both a test log and their production log. Now, in certificate transparency, we identify logs by their public key. So by having 2 different logs with the same key pair, any tree heads produced by either would then be considered to be from the same log by the ecosystem. So what happened in this case was the test log produced a tree head, and then the production log produced a different tree head because it contained different certificates. And these 2 tree heads were assumed to be from the announced production log. But when asked, the production log was unable to provide one of these tree head consistency proofs. And that was how we figured out there was something funny going on. In the second case, the second log that had this problem, they had a similar problem where they couldn't produce a tree head consistency proof for 2 tree heads, but for a different reason. Now, this log just happened to be running on AWS during the recent S3 outage. And what happened was they published a tree head, S3 went down, and with it their log instance went down. And then, in an effort to restart the log and get their system up and running again as fast as possible, they actually ended up loading an incorrect and older backup of the tree data that didn't contain all of the certificates that were needed to create the latest published tree head. Then, before they were able to rectify this and restore the correct backup, some certificates came in and an inconsistent tree head was signed. Now, the log operators of this particular log, they responded to this impressively fast. This inconsistent tree head was actually only being served for something like 2 minutes. And after this had happened, they then published a very detailed post-mortem on the incident to let the wider community know what had happened. Now, in the certificate transparency community, we really pride ourselves on transparency. And so when incidents like this happen, we really encourage discussion about what happened, why it happened, how it happened, and what should be done next to remedy it on public mailing lists. We encourage this because certificate transparency is still young, and we're still learning. And for every single one of these war stories that I present to you today, we have learned something new about this ecosystem that we are building. OK, so certificate transparency seems like a great idea, right? But how can we incentivize people to adopt it and get it used quickly? How can we incentivize people to get as many certificates as we can into certificate transparency logs so that we can start reaping the benefits of this system as soon as possible? Well, that's where Chrome comes in. Currently, Chrome requires that a specific subset of certificates called extended validation certificates be present within trusted certificate transparency logs for their websites to be displayed as secure. As of April 2018, Chrome will require that all certificates be present within trusted certificate transparency logs for their websites to be displayed as secure. So this is a huge milestone for us. It's kind of a big deal. But I've said they have to be in trusted certificate transparency logs. How does a CT log become trusted by Chrome? Well, Chrome has a log policy, and certificate transparency logs have to meet the requirements of this policy to be considered trusted. And there are things in this policy like the certificate transparency log has to conform to the certificate transparency RFC, has to maintain a 99% uptime as measured by Google, and a whole handful of other things. Now, one particular requirement of this log policy is that when a certificate is submitted to a certificate transparency log, it has to be fully incorporated into the log within 24 hours. The point of this requirement is to minimize the time between when a certificate is submitted to a log and when it is then made visible externally for anyone monitoring the log, whilst operationally still allowing some wiggle room for the amount of time needed to incorporate the certificate into the log tree. Now, you might be sitting there thinking, 24 hours is quite a long time, right? How long can it take to incorporate a certificate into a tree? And for the most part, you'd be right. Most of the time, that's way more time than is needed. But what this really is the amount of time allowed for log operators to recover when something goes wrong with their log. We saw from the second war story that I presented, with certificate transparency logs, when recovering from failure isn't as simple as just restoring from a backup. Usually, when something goes wrong, some sort of manual intervention is needed. And if the thing that goes wrong happens at 3 a.m. on a Sunday evening, trust me, your log operators are going to be very happy they have this 24-hour window to rectify the problem. That being said, even 24 hours isn't long enough for some logs. So one log actually easily incorporated the specific certificate in question into their tree within 24 hours. But the problem was they had an issue with their certificate inclusion proof API endpoint that meant that externally, people couldn't actually retrieve the certificate until 36 hours after the submission date. The second log that struggled with this 24-hour property was actually one of our Google-operated logs, and we simply didn't manage to incorporate a whole bunch of certificates into the log tree within 24 hours. Now, what happened in this case was an external group who we regularly converse with, who also have a huge collection of certificates, realized that a lot of the certificates they had, we didn't have in certificate transparency logs. And being the wonderful people that they are, they decided to help us with our goal of having all of the certificates in certificate transparency logs, and they decided to submit these certificates to our logs. And they submitted all of them at the same time. And it's pretty safe to say that this was the largest load test our logs have ever had. And this resulted in a huge backlog of certificates waiting to be sequenced and then reliably stored. And unfortunately, because of the time it takes to meet the required level of consistency when storing entries in certificate transparency logs, this process was still going on more than 24 hours later. But it's not all doom and gloom. Most logs have no problem with this 24-hour time limit, and they're all sort of still pottering along happily. OK, so the big question, does certificate transparency actually work? Well, it's unlikely we would have been invited to speak at an event like this if we had built the system and it was failing at life. So yes, it does. Google runs a monitor to keep an eye out for Google certificates. And we detected that a specific certificate authority had issued a certificate for www.google.com that we had not asked for. Now, after having a chat with them, it turned out that this certificate was created for internal testing purposes. And whoever it was creating their testing certificates had sat there and gone, I need a domain for my certificate. What shall I use? Oh, I know, www.google.com. And this is bad. You should never use a real domain that you don't own for a purpose like this. And although they claimed, just for testing purposes, it was only in our testing environment, it clearly got out of the testing environment because we found this in a certificate transparency log. Now, luckily, the certificate was only valid for 2 days because it was a testing certificate. But that being said, the repercussions of this action on their part was that Chrome now requires for all certificates issued by this certificate authority that for their websites to be displayed as valid, those certificates have to be in trusted certificate transparency logs. Another example of certificate transparency working is based on a blog post from our wonderful hosts, Facebook. So it turns out Facebook also runs a monitor on certificate transparency logs for Facebook domains. And what CT helped them to discover in this case was that one of their teams had a whole bunch of certificates for Facebook subdomains issued by a certificate authority that wasn't Facebook's main certificate authority vendor. Now, although this wasn't a malicious incident, certificate transparency did allow Facebook to detect this and then take the appropriate steps to get these certificates revoked. If you want to know more, go and read the blog post. So, before I'm able to tell you what's coming next for certificate transparency, I just need to tell you a little bit about where we are currently. So, back when Google was first trying to get certificate transparency off the ground, we needed to prove that it was possible to build and run reliable certificate transparency logs. After all, if Google couldn't successfully run a log, we had no hope of convincing anyone else to get involved too. So with that in mind, the first, and what is actually current, implementation of certificate transparency logs were built to be extremely reliable and robust to infrastructure failure. So the whole Merkel tree was both stored in and served from RAM. And now, this was OK back when log sizes were somewhere around 2 million certificates. But now, when everything's beginning to shift over to HTTPS, and also with the increase in popularity of both free and short-lived certificates, log sizes are starting to increase to a point where keeping the whole Merkel tree in RAM is probably not going to be viable in the very near future. This is a graph of certificate transparency log sizes. It starts about 2 years ago, where the largest logs were roughly 5 million certificates in size, and goes all the way to today, where we're looking at 90, 95, 100 million certificates within one log. And in between those two times is this big, scary growth curve. So what are we going to do about this? Well, we are developing a new scalable Merkel tree implementation called Trillion that can be used to back certificate transparency logs. In this implementation, the Merkel tree is stored and served from a database, so it can be scaled much further. In fact, so far, we've managed to test it to more than 3.5 billion entries, and it's still going strong. Trillion is open source, so external people can use it to back scalable certificate transparency logs as well. In fact, the 2 tech companies that I mentioned earlier that are just in the initial stages of spinning up their own logs will be running Trillion-backed certificate transparency logs. One thing I have to mention about Trillion is that it's actually not just certificate-specific. So as it turns out, general transparency and the verifiability properties that the Merkel tree provides have a lot of uses outside of certificate transparency as well. For example, there are projects currently going on using Trillion for things like key transparency, binary transparency, and even the UK government is interested in using Trillion to help prove the integrity of some of its registers. Then, in addition to this log mode that certificate transparency uses, Trillion also provides what we like to call a verifiable map. Now, a verifiable map is a verifiable key value store built using a complete Merkel tree that has 2 to the 256 leaf nodes, most of which end up being empty. To add a key value pair to this map, what you do is you take the SHA-256 hash of the key, and that hash gives you the leaf index at which to store the value. Now, using those 2 proof mechanisms that I mentioned earlier that the Merkel tree data structure provides you, the map can then prove that for a given key value, it does or does not contain a specific value. Use the word value lots. So why am I telling you about these verifiable maps? Why do you care? Well, if we go back to certificate transparency, say you're a small business owner, and you have a domain, and you want to know about certificates that are popping up all over the place for that domain, but you don't have the technical capability to monitor certificate transparency logs yourself. Well, something that large companies are starting to do these days is offer log monitoring as a service. But then, these small business owners have to trust the monitor to tell the truth about whether they have seen certificates for your domain or not. And, one of the sort of key points of certificate transparency is to get rid of this need for blind trust in the system. But if the monitor was to use a verifiable map to store the certificates that it saw for certain domains, then when a small business owner comes along, it could prove to the business owner whether it has or hasn't seen certificates for their domain. So, the verifiable map is an important piece in the certificate transparency puzzle. And finally, I alluded to this earlier, we need more big tech companies to get involved and run certificate transparency logs. We need more logs run by people who have experience running internet scale systems. So please, 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 get involved, run a log, and help make the internet more secure. Okay, so now I'm going to invite the tech lead of certificate transparency to come and join me on this little stage, and we will take any questions that you may have.
Hello.
This is Al. I didn't say his name. This is Al.
Questions?
May have been a wasted walk.
So I actually, go ahead. There are a couple right there.
Yeah, I was just wondering if I have my own certificate authority that I use for my own space, and I use Chrome. Once you start requiring logs, how does that work? Does the CA automatically update these logs for the Chrome to use?
So you're talking about your own private CA?
Yes.
Yeah, okay, so at the moment, the way that Chrome will deal with that is if Chrome is being used in an enterprise environment, for example, there are configurations to provision private CAs, and so CT won't be required for those.
Okay.
When you added certificate pinning to Chrome, you had a bypass for locally installed root CA. So will that continue to hold true once you go to this model?
To be honest, I can't really talk for Chrome. We are a separate team, and you'd get a better answer from Chrome. I believe that that's true, but you need to talk to Chrome.
What about the other browsers? Is anyone else using this, or is it just a Chrome thing?
Currently?
Anybody from one of the other browsers here who might like to comment?
Oh, yeah.
Okay, so Mozilla has partial CT implementation at the moment. Watch this space.
So how many such logs do you have to look for? So if you are a domain owner, how many sources of these logs do you have to continue to scan? And
so the monitors, you mean? Right. So I mean, essentially, the monitors have to watch the majority of logs that are trusted by the browsers. So, for example, Chrome. Okay. So we don't envision there to be, thousands of logs, right? We expect sort of tens tops, which is why it's important that we have companies that know how to operate software at scale running them. So if you look at the Chrome policy, Chrome requires that certificates are logged to a certain number of logs based on the lifetime of the certificate. So that isn't going to be all of them, it's going to be sort of 2 or 3. So the monitors do need to check the logs.
so just to clarify then, so there are monitors that are monitoring the logs that are coming from the certificate authorities, right? So, and then there is, let's say, the domain owner, Facebook or Google. So when they come up with a new certificate for their system, they get it signed by the a specific CA, right? And then, so there are, let's say, how many monitors are out there that are looking for? Isn't there like a combinatorial problem of the number of monitors and the number of these log providers, or actually not log providers, CAs, certificate authorities. So you have multiple CAs that I go to, to get my certificate signed by, right?
Yeah.
And then you have multiple monitors that monitor all of these CAs.
So just to be clear, you've got the CAs who you go to get your certificate signed.
Right.
And whenever they issue something, they will put these certificates into certificate transparency logs.
Right.
And like all of the CAs are logging to whatever, so there's a different set of people for the certificate transparency logs. And then the monitors are monitoring the logs, not the CAs.
Oh, okay. So then how many number of these CTLs that are running? What's the...
How many logs are there?
Right.
Some.
At the
Less
moment,
than
there
20.
are
Okay. So all the CAs push their data to these
the logs.
logs,
Yeah.
and then everybody monitors these logs.
Yes.
Yeah.
Okay.
Yes, that's how it's meant to work.
Thanks.
Hi. What clients are passing the certificates that they're seeing in the wild in? It sounds like, is it just Google's crawlers, or is it random clients in the wild reporting in on certificates seen on the open internet?
So we fill it from Google Trawler, and then, as Kat mentioned, there is another project that does this sort of scanning of the entire internet space, and comes up with the buckets of data.
Okay. The reason I'm asking is because if there's an MITM attack that is targeting specific users, it's unlikely that Google's crawler would see that, right?
Well, yeah, so to be clear, like a lot of the certificate authorities directly push their certificates to certificate transparency logs as well. But also, it's the endpoint that accepts certificates is public, it's open, so anyone can submit to them. Like, who does in reality is sort of, is maybe the question you were asking, but anyone can. It's wherever the microphone goes.
One question about certificates that expire or have to be revoked for some reason. So will they continue to be in the transparency logs, or can you recalculate at some point?
No, the whole point of the logs is that they're append only. Yeah. You can't pull things out, otherwise that breaks it.
Okay, thanks.
So, for the mobile applications which are directly communicating to the servers, does this hold true for this certificate transparency logs are applicable for them as well, or this is only with the browser integration?
Currently, yeah, we're just focusing on the browser, but you could totally imagine mobile applications that are using services over TLS to require this too.
Do you expect this is going to break a lot of security gateways on the egress side, such as proxies that do SL decryption to prevent malware, etc.?
No. This is a slightly more complicated thing that we could talk about later on, but essentially right now, the majority of the CT data is embedded inside the certificate that's issued by the authority. So it's kind of just transparent, I guess.
So these gateways usually issue, sign the certificate so as to make the.
I see what you mean. Sorry, you mean like proxies to crack open?
Proxies,
yeah. Well, yeah, right. Unless they publish their certificates to the CT log.
Okay. So for every single domain that gets decrypted, you will have 2 entries, and then somebody will be monitoring this, and then they might call it out. And every single corporation that is going to, network that's going to sign their own certificates is going to add another entry. So it's going to explode, right?
Well, so I guess if you're doing this in an enterprise situation, then the caveat earlier on where you provision, your internal private CA to all of your desktops, that would presumably route.
Oh, I see. So private CAs are not required to publish the logs then?
Yeah, I'm pretty sure that that's the current policy is that.
The Chrome will detect such logs, or?
Well, so Chrome, I believe, has mechanisms for provisioning, private CAs for enterprise. Like, there's a whole bunch of enterprise configuration stuff that you can do with it. And I'm not particularly familiar with all of this, but I'm fairly sure that the hook is in there to do that. And if you do that, then CG won't be required for stuff routines.
Okay, thanks.
Curious, the trust is still in the certificate authority. Is there any work being done to improve that level of trust? Because it seems like the log is just trying to make sure that they're operating properly, right?
This is, there's lots of work being done in this area, right? I suppose I can't really talk to this too much.
Okay, great. Thank you all very much. Thank you all.